Hi, in this video I'm going to give a quick demonstration of a web app that I developed for designing and visualizing digital features, and at the end of the video I'm going to give an overview of some of the implementation details of the web app. So this is the GitHub repository of the project, and here you can find some information regarding how you can install the software. To use a web app, you can simply visit the link that I provided here. This is the web app, and on the left side you can see a menu and click on each one, redirects you to the corresponding panel to design a filter either via zero pole placement methods, FIR filter design methods, or IR design methods. For the zero pole placement method, I can specify my desired locations of poles and zeros on the Z plane. For example, if I want to design a low pass filter, I can place my poles near omega 0, and if I click on design filter, the web app gives me the magnitude of the frequency response of the filter, the phase of the frequency response of the filter equation, and also the output of the filter when it is subjected to various test signals. And for each test signal, I can add Gaussian noise or remove Gaussian noise on the signal. And for the FIR design method, I can first choose my desired filter type, which can be either low pass, high pass, band pass, or band stop. And for low pass filters, I can specify the cutoff frequency to be, let's say, 0.5. Next, I can choose a window type to be either rectangular, Hamming, hand, or Bartlett. Lastly, I can choose my desired filter size to be, let's say, 20. And when I click on design filter, the web app gives me the magnitude of frequency response, filter coefficients, and as before, the output of the filter when it is subject to various test signals. And as you may have noticed, the web app doesn't show the phase of the frequency response because for FIR filters, the group delay is constant. And for IR design method, as before, we can first choose the filter type, then the design method, which the web app currently supports the Butterworth method, then the cutoff frequency and the filter order. And when I click on design filter, the web app gives me the magnitude and phase of frequency response, the filter equation, and as before, the output of the filter when it's subjected to various test signals. And as we can see here, for IR filters, a small filter ordered like 5 gives a relatively good filter in terms of having a sharp transition between the passband and stopband, but the trade-off is that we have dispersion in the phase. Now I'm going to quickly talk about the way that the web app translates the locations of poles and zeros that the user specifies on the Z plane to the actual filter equation. So the way that it works is that, let's say the user specifies some zeros and poles on the Z plane. What it actually means is that they want a filter with the transfer function of this form. And here M0, M1, M2, etc. they correspond to the zeros of the system that they place on the Z plane, and P0, P1, P2, etc. they correspond to the poles of the transfer function that is specified on the Z plane. And to convert the transfer function of this form to filter equation, we have to first multiply the terms in numerator and denominator together to reach something with this form. Let's say 0.4 times Z raised to the power of, let's say, 5 plus another number, let's say 0.1 times Z raised to the power of 4, etc. A term like that in the numerator and similar terms in the denominator. And we can easily go from the transfer function with this form to the actual filter equation by shifting the samples, which either would be shift of X signal or Y signal, depending on whether the term is in the numerator or denominator, by the power of Z, which is, for example, in this case will be 5, for this term will be 4, etc. And to perform multiplication between these terms, the way that the web app performs this is it first creates a set of lists, which they have this form, etc. Similar lists for the numerator and similar lists for the denominator as well. And then the web app computes the convolution between the terms from left to right, once for the numerator and once for the denominator. So for the numerator, with a for loop from left to right, it first computes the convolution between these two terms, and then it convolves the result with the third term, so on and so forth. It does that once for the numerator, and it performs the same operation for the denominator as well, and that gives the actual coefficient of the transfer function, which we would get if we had multiplied the terms in numerator and denominator together. And for the FR design method, the web app follows the classical method of windowing method, which can be found in various textbooks. And for the AI design method, the web app also follows the classical method by first computing the coefficients of an analog filter, and then it converts that to a digital filter using bilinear transform. Thank you for watching, and stay tuned for more updates on the web app.